Okay, so I'm going to get started. Today's announcements are pretty much just exam-related stuff. So the exam review is going to be 2 to 4 p.m. Sunday in Math 100, and the exam is Tuesday night, 7 to 9 p.m. in Chem 140. I'm hoping I can get through all of the reactions in this chapter by Friday. I probably won't finish the synthesis problem from the notes, but I figure that's kind of a review anyway. So if that happens, then all of Chapter 19 will be fair game. If it ends up that we're running short on time, then I might end up cutting the last reaction, Wittig synthesis, which will then, I guess, show up on the next exam. So pretty much end of Chapter 16, which is like directing effects, up through wherever we get in Chapter 19 by Friday is kind of what's going to be on the exam. Any questions about that? All right, cool. All right, so last time we looked at a couple of reactions for aldehydes and ketones. We got up through reduction by a few different methods. Today what we're going to look at is reactions with organometallics. Okay, so we introduced Grignards and lithiums a way back, like partway through OChem 1. We haven't done that much with them. Pretty much all we've done with them is, first off, react them with water. So like R, MgBr, and RLi. If you react either one of those with H2O, you pretty much just get an alkane back. Because if you remember, these both act like, you could draw them either as the covalent form, or you can draw them as R minus, and then the metal plus. So whatever the R minus is just goes and rips a proton off of pretty much anything that has a remotely accessible proton. They're very strong bases. They really want to get an H back. The other thing that we've done with these is send them to go attack epoxides. So again, these act like very strong bases, good nucleophiles, so they can go in and attack and do a ring opening in an epoxide. I'm going to do a review on that real quick, but I'll do it at the end of this section so I can contrast it with the new stuff that we're going to cover. Okay. So in this section, because the chapter is about aldehydes and ketones, we're going to look at organometallics plus aldehydes and ketones. And the mechanism for this is actually pretty similar to what we've been seeing elsewhere in the chapter, where you have some kind of carbonyl thing, and you send in a nucleophile to attack on the base of the carbonyl, and it makes a new bond there. Here, the nucleophile that we're using is actually the R minus of the Grignard or organolithium. Like always, Grignards and organolithiums need some kind of ether solvent to be stable, so usually you would explicitly write that on the arrows. So I'll sort of show that afterwards when I put up the overall reaction. Okay, so we take our R minus. I'm actually going to call this R prime, just to emphasize that it is actually different from whatever groups we have on there to start with. We attack on there, we kick up to the O, just like everything else in this chapter pretty much. And now we have a new R group on there, so we just made a new carbon-carbon bond with any R group of our choice. So this is super useful and versatile. This is a good way to put together parts of your carbon skeleton. Okay, at this point, obviously we're not going to have any protic stuff around while we're doing this reaction, because if we did, this would just go rip an H off instead of doing anything useful. So at this point, the molecule just kind of sits around like this for a long time until we find, dang it, until we finally get around to doing a water workup, H3O plus, and then this can come in, rip an H off of that, and get us to here. So basically we're getting a new alcohol out of it, but it's an alcohol with one more R group attached to the carbon than we had to start with. Okay, so questions about that? All right, cool. Yeah, the mechanism's actually like real simple. It's just the implications turn out to be kind of a lot of different possibilities here. Okay, so overall reaction here, before we get into how to like do retrosynthesis, it's going to look like whatever aldehyde or ketone. Step 1 is going to be our Grignard, and then we're going to explicitly write the solvent for this one because it does turn out to be crucial for success of this reaction. And then 2 is just going to be our water workup. So that gets us to here. Or pretty much exactly the same thing for alkyl lithiums. So one, you could use RLI and THF, and then do a water workup, and then get your R prime on there. Okay, so that's kind of how it's going to look overall. And note that, yeah, this absolutely has to be a step 1, step 2 process. If you don't include those, you're saying that you're chucking all of this into the flask at the same time, and that's going to just go rip a proton off of the water and is not going to do anything useful. Okay, so where this gets complicated is in doing retrosynthesis. Because we now have an alcohol with 3 different R groups coming off of it. If I just tell you to make this molecule, any one of these R groups could have been one that came in as an organometallic, depending on like how many different types you have. So say I want you to make that thing. You can do the disconnect, like the cut here line, on any one of these 3 different R groups coming off of here. So I'm going to call these like disconnect 1 or disconnect 2 or disconnect 3. I could come into this from either basically this with any 2 R groups on there, and then the third comes in as an organometallic. So I could do like this and this, or this and this, or this and this. All right, so that I wrote that out pretty fast, but basically if you just like snip any one of the 3 alkyl groups attached to that central carbon and have that come in as an organometallic while the other 2 are on the carbonyl to start out with, you can sort of work this backwards 3 different ways, which opens up a ton of different options when we're trying to do retrosynthesis. Okay, so questions about this? Yeah?
Is there any one option like between the 3 of those that would kind of like make the reaction proceed quicker?
Probably sterics is going to speed it up or slow it down a little bit, but honestly, like these organolithiums and Grignards are so reactive that it's going to be like over before you know it either way. So yeah, there's pretty much like no practical difference that would make us pick one over the other. So then it just comes down to like, I guess out of these carbonyl compounds, like which one is the easiest to make from whatever starting material you're given, or which one fits the limitations of the synthesis. I guess like, how could I set this up? Maybe if I said like, make this molecule from pieces containing at most 6 carbons, for example, then that's ruling out this one and this one, but then like this combo would work okay.
So you like set us up always.
Yeah, or I'd leave it so that all three were valid options and then they'd all be graded correct. Yeah, so there's like pretty much no reason to pick one over the other unless there's additional criteria given. Yeah?
Now, which organometallic is the hardest to make? Like, would that be a factor?
Honestly, they're both pretty interchangeable as far as we're concerned. And that's going to continue to be the case up through, I want to say, chapter like 22 or 23, where we finally start seeing differences. Yeah, that's pretty much like if you've got lithium metal or magnesium metal in your lab at that point. Okay, so other questions about this one? All right, cool. So I mentioned that we did use these organometallics in the past for attacking on epoxides. Let's kind of take a look at the difference between this reaction and stuff with epoxides and see how the retrosynthesis looks different between them and how you can tell which one you want to use. So, organometallic on carbonyl basically looks like okay, and for this one I'm going to use an aldehyde, so one of my R groups I guess is technically an H, but all of this stuff up here still applies. But if I'm trying to do working backwards, if I tell you make this compound from maybe like phenyl lithium plus some other compound or phenyl Grignard, the tip-off here that you used a carbonyl is that when you draw the disconnect, the OH is on the first carbon past the disconnect. God damn it. This chalk is not good. Okay, so the tip-off that you're doing this on a carbonyl with whatever organometallic that you have is that the OH is on the first carbon, which totally makes sense because when we do this attack, the organometallic is going straight in for the carbon at the base of the carbonyl. By contrast, if we're doing organometallic on a cuprate, not on a cuprate, on an epoxide, so if again I tell you use some sort of phenyl organometallic reagent and make this compound, working backwards you're going to be able to tell that you had to attack an epoxide because here the OH is on the second carbon away from the disconnect. So in this case, the epoxide that we'd use would have to be this thing. So basically like break this disconnect and then have the OH or the oxygen sort of make a three-membered ring back onto like the carbon right next to the disconnect is how you want to work backwards through this. So like carbon 1, 2 gives you carbon 1, 2. Can I use a Grignard or organolithium to do this? Right, probably not. I guess I'm leaving it vague what R is, but if R has any H's on it, like at the beta position, then Grignards and lithiums are a bad choice here. This is why we introduced cuprates. So in this case, I would probably have to go turn my phenyl lithium into a cuprate if I wanted this to work. Okay. So you might be able to get away with this depending on exactly what the epoxide is if there's no H's on the carbon one outside the ring, but probably better not to risk it. Like cuprate's never going to not work. Yeah.
So with the normal epoxide, your lithium's fine, like without an R group?
Exactly, yeah. Yeah, or anything with, so like this unsubstituted ring is okay, or anything where the R groups attached to the ring don't actually have any H's, like in this position right here. So like phenyl would be okay, T-butyl would be okay, but most anything other than those and Grignards and lithiums are a bad idea. So good question, thanks. Okay. So basically, cuprate's probably the safe option, and it's always going to be an okay choice for this. Okay. Questions about that part? Yeah. Yeah, pretty much cuprates. Like if you have an epoxide, you can't go wrong with a cuprate. So it is probably the safe option. Yep. Okay, so then one more combination of like attack carbon to make a new carbon-carbon bond kind of synthesis stuff is again kind of tying together things that we've seen earlier. And that is pretty much any role that we've seen these organometallics, either Grignards or lithiums or cuprates doing. We can also use an acetylide instead. So a deprotonated alkyne, I guess, is also technically an organometallic, like the counter ion on there, even though we don't always show it, is technically sodium because we usually make it with NaNH2. We've seen that you can use acetylides to attack epoxides and that it works just fine. And then you have your new alkyne attached to the epoxide. Turns out you can also use acetylides to attack aldehydes and ketones. So they go after a carbonyl just the same as a Grignard or lithium does. So like, whatever acetylide that you wanted to make, and I'm showing this as an H, you could do whatever R group on there instead. H3O plus. Will get you pretty much an equivalent to what Grignards or lithiums did. The only telltale is that one of the R groups is triple bonded on like the carbon that just did the attack. So basically, you can use acetylides to do either one of these. The only difference is whatever the new R group is, it's going to come in as an acetylide, and then you don't actually have to bring it in with a magnesium or a lithium or a copper on there. You can just bring in whatever deprotonated alkyne because these things are a lot weaker bases, at least comparatively to whatever other R group that you would normally turn into an organometallic over here. Okay, so I think there's one sapling problem where you actually end up having to do a synthesis. It's like those drag and drop stuff into the boxes on like the arrow kind of problems where you end up using an acetylide to attack a carbonyl. Okay, questions about that one? Yeah?
If you wanted to further manipulate that, could you use like a base that's strong enough to only deprotonate DOH and not the acetylides?
Yeah, so you totally could. So I guess this is, so I guess just sort of following off on where we can go from here. We can pretty much treat the OH and the acetylide orthogonally and like do different chemistry to them as long as we're careful that it's reagents that only affect one or the other. So if we wanted to protonate this one with a pK of like 16-ish and not this one with a pK of 25, we just need a base that'll pull this off. pK about 20 or like the low 20s is a good choice. I don't know if we've covered any in that range actually, but yeah, because usually if we wanted to deprotonate this, we'd use sodium hydride, but I think that's going to be a problem down here. Yeah. Well, let's finagle that, and now it's not an issue. Okay, but yeah, from here you could do whatever to the OH group. And you could also do like whatever additions to the alkyne that you wanted, because we just saw a bunch of those in chapter 14. Okay. So other questions about this? Okay, cool. Alrighty, so the next part of the chapter that we're going to get into is also a reversible addition kind of a thing, but there's a lot more going on than just reversible additions because it turns out we can do a ton of extra stuff with these reactions, so they sort of get treated as their own section. So what we're looking at here are acetals and hemiacetals. Okay, so the mechanism for these, hemiacetals at least, is going to be the same mechanism as it was for hydrate formation or hydration. So you can use either acid or base. But instead of using just water, we're actually going to use an alcohol. So whatever ROH instead of H2O. Okay. So if we're doing acidic acetal formation, no, sorry, acidic hemiacetal formation. We just got to stick a proton on there first. Make the carbonyl more electrophilic. And now instead of water coming in, we're going to have ROH come for it. And then now instead of H2O plus hanging off, we've got ROH plus hanging off. So we just have to deprotonate that oxygen. And we get to something with an OH and an OR. I guess I didn't explicitly draw up acetals and hemiacetals, but hemiacetal has an OH and an OR. I guess I did at the start of the chapter, though. Okay, so basically, if you know the hydration mechanism, you already know this. It's just there's an extra R group involved instead of a proton. Okay, questions about that one?
Just a quick one on the concerted step or the alcohol attacks.
Uh-huh.
Why isn't that shown as a separate carbocation formation since we're in acidic conditions?
Good question. So why don't I show a carbocation? So this is actually a resonance form of the form that I do show. Out of the two resonance forms, left or right, yeah. Yep, yeah, this one's the major. So you could show it this way, and regrettably, I think there are a couple of sapling problems that actually do have you show it that way, but really it's going to be like this most of the time. Okay, other questions about that? Okay, cool. Alrighty, so that's an acid, in base. So for this one, instead of OH minus, like we did for hydration, we're going to use OR minus. And just go straight in for the attack. And then just like we did in water, to finish up, this thing needs to go take a proton from the conjugate acid of whatever the base is that we attacked with, so alcohol in this case, goes and gets an H. And that gets us to here. Okay, so that should hopefully be fairly reasonable and sensible looking to you guys. Any questions about those two? All right, cool. So where we start to diverge from the stuff that we saw earlier in the chapter is, for one of these, where in acid, what do we know about OH groups in acid based on OChem 1 chemistry? We've seen reactions before where we can stick a proton on here and do an elimination and get that OH group off the molecule entirely. I guess convert it to a leaving group might be a better way to phrase that. So let's cut back to this acidic mechanism, because we're still in acid. We can protonate that guy. Get to here. As a side note, we could also protonate the OR group, but if we did that, we'd pretty much be walking backwards and getting back to the carbonyl. So we're kind of only focusing on a path through this mechanism that gets us a noticeably different product instead of just like backing up to where we started. But odds are pretty good that all possibilities are going to happen here. Okay, so we protonated the OH group. If you remember from OChem 1, at that point it's a good leaving group and can drop off. But something's a little bit different now. If we just did that, we'd end up with a carbocation. And we already know that carbocation is not too likely to form if you've got something with lone pairs right next door that can help stabilize it. So instead of just showing this dropping off and making a carbocation, we're simultaneously going to have the lone pair from the OR group come down to help it out, which gets us to, I'm going to actually like invert this carbon real quick first, which gets us to here. And we've just kicked out a molecule of water. Okay, so at this point, the water could come back, attack here, because if you look at this, this is looking pretty similar to a protonated carbonyl. The only difference is instead of having a double bond to an oxygen with an H on it, down here we have a double bond to an oxygen with an R on it, and that R is probably not coming off very easily. So we're not going to like be able to deprotonate this. We're going to have something else come in and attack. That could be water, which would get us back to the hemiacetal, or just statistically more likely based on what reagents we have around, it could also be another molecule of ROH. So that can come in, kick that down. And that'll get us to here. And then we could just deprotonate this and get something with two OR groups on it. Okay, so take-home message, in base, you're going to stop at the hemiacetal form. Basically, stop here in base. But in acid, you're going to get the hemiacetal briefly, but odds are pretty good it's not going to stick around for very long. You're just going to shoot straight through all the way to the acetal. Okay. And then all of these steps are reversible because if you look at it, the group that we're kicking out and the group that we're adding on are both like fairly similar pKa's and similar behaviors. So if you want to do hydrolysis, you can sort of drive it back towards the starting material as well. So basically, acetal formation, you want Le Chatelier on your side to drive it as far towards the product side as possible. So if you want to make as much of this as you can in this equilibrium reaction, you want as much ROH as you can around. So basically use alcohol as a solvent traditionally is how this is done. And then you want a little bit of acid around for a catalyst. And we also, because we're spitting out a molecule of water during this reaction, we want to minimize how much water there is around to accidentally drive this thing back to the starting material side. So we're going to use something that's good at soaking up water. And I've used this in OChem 1. I don't know if people who took OChem 1 with other people have seen this, but 4 angstrom molecular sieves are a good way of doing that, just soaking up the water in the reaction. There's a few other options too, which you might have seen in the exam archives, but this is kind of the way most people do it now. Okay, so you're driving to the acetal side. These are the reagents you want to use. If you're driving to the carbonyl side, this would be acetal hydrolysis. So you're using water to break up the acetal. So here you start out with your acetal, and you want to go back to your carbonyl. Here you want the opposite circumstances, as much water as possible. And again, acid catalyst, so we can just combine those, H3O+. For both of these, sometimes people write it explicitly, sometimes they don't, but a little bit of heat kind of helps the reaction go. You can write heat on the arrow if you want. Okay. So questions about this set of reactions? Okay, so you might, oh yeah. Mm-hmm. I know there was one reaction from OChem 1 where we wanted to get rid of water. I'm trying to think what it was. I think it might have been, oh, acid catalyzed ester formation maybe, where I think I introduced it there, where you have like 2 of these guys and you do like H2SO4 and you're making like this thing, but you're also making a molecule of water. So if you want to force it to go to the product side, you lock away all the water in 4 angstrom molecular sieves. I think that might have been the reaction where I talked about these before, but there might be a couple others. Does anyone remember offhand? I don't. Okay, cool. Well, it shows up in a bunch of places. Basically, anytime you need water like tucked away from your reagents, 4 angstrom molecular sieves is a nice way to do that. Okay. Uh-huh.
So the acid source for the acetal formation, can we not use H3O+ because it's formed water?
Mm-hmm. Yes, so usually what you'll do is add just a tiny amount of catalytic H2SO4. So yeah, in that case you would not write it. So basically like H3O+ is like explicitly like an acid source and water. So usually this is like sulfuric acid in water. Here if you're writing H+, then that's like sulfuric acid added to ROH. And the reason sulfuric over other acids is because the counterion, the HSO4- is like the worst possible nucleophile and is not going to hang around and cause any problems reacting with your molecule. Okay. Uh-huh.
So can you explain again why water would come back and attack so that
Oh, here? It totally would, yeah, that's the problem. Like, unless you get this pulled out of the way and like locked up in the 4 angstrom molecular sieves, yeah, it's going to just like equilibrate back and forth along this whole reaction and like back to the carbonyl. And so the only way to like force it to stop over here is just to remove any option of it going backwards through the mechanism by taking away the water that it needs. Yep. Yeah, and that's the case for a lot of equilibrium reactions. Like that's kind of why I say like we need to get Le Chatelier on our side, and that's just by like pulling the equilibrium towards one side or the other by either having as much as possible of something like the ROH or as little as possible of something like water. Yep. Yeah, good question. Thanks. Okay, so you might be wondering why we're bothering to look at this at all, because it's pretty much the same as hydration. Turns out this is actually incredibly useful and is the first example of what we're going to see actually it might be the only example of what we're going to see, but it's the most useful example of stuff in this category, which is called protecting groups. Okay, so what we've got here is a way of taking a carbonyl, making it look like something else for a little while, and then later on, under conditions of our choosing, turning it back into a carbonyl. So if we're trying to do some reaction under conditions that we don't want to react with a carbonyl, but we know it's going to mess with the carbonyl anyway, what we can do is sort of take our carbonyl, cloak it as an acetal for a little while, and then later on decloak it or deprotect it and get the carbonyl back. So okay, so there's like hundreds and hundreds of different protecting groups, and there's this actual like encyclopedia online that's really cool that has like this whole color-coded chart of like, here's what protecting groups work on what functional groups and what conditions they come off on, and here's what you can deprotect in the presence of other groups. This is probably the most useful and like probably one of the oldest known protecting groups, and it's the one we're going to see the most of. Okay, so how this might look. So say you're trying to turn this thing into this thing. Okay, so looking at this, we're making a new carbon-carbon bond right there. What kind of other molecule am I likely going to have to attack with my starting material in order to make this group be on there? An epoxide, right? Because at the disconnect, the OH is on the second carbon away. Okay, cool. So let's attack an epoxide. I'm going to take this, make it into something that can attack an epoxide. So why don't I just lithium THF. Why don't I make that? What's going to go wrong? Exactly, yeah. This thing is just going straight in as soon as it forms. Because we know that organolithiums also go after carbonyls. So, whoops. That's not what I was going for. Okay, so if we want to do this organometallic this organometallic chemistry in the presence of a carbonyl that we don't want to have affected by this, we're going to have to cloak or protect this carbonyl, do our thing, and then deprotect it at the end. Okay, so instead, so that's not going to work. So protect that first. Okay, so what I'm going to do instead is, I'm going to bring in, I don't even have to be specific about what the R group is that I'm using, because we'll cover some specific examples that work particularly well for this. But you can, if you want, just leave it as ROH, because in the long run it doesn't matter. That RO group is going to come back off the molecule anyway. Okay, so we want to have ROH, acid, 4 angstrom molecular sieves. We are going to protect this as the acetal. All right, now we are safe to make our organolithium because none of the organometallics that we've looked at will actually go after acetals at all. Okay, so we have our organolithium here. If we want, we can do the step where we turn it into a cuprate. Is that going to be necessary for this particular synthesis? Right, yeah, you're doing this on the simplest possible epoxide. You can actually get away with kind of half-assing it, I guess, and not bother making the cuprate. So let's just go straight in for the epoxide at this point. Oh, I guess in the notes I use the Grignard instead of the lithium. They're fine either way. Okay, so now we do epoxide and then, so this is one kind of small detail and there's some choice in how you write this. So normally if we did the attack and epoxide first step, that would get us to this initially. And after that, we're used to doing a water workup of H3O plus, right? Which is just going to stick an H on there. Depending on how much you heat this up, you can get away with doing the water workup, sticking the H on here, and if you're quick about it, it won't actually hydrolyze your acetal. But since we know that we're going to have to hydrolyze the acetal anyway, we can show it as 2 separate steps or as a single step. So you could just skip this and show it going entirely to the product at the end. And really it comes down to how long are you letting it sit around in your acidic water conditions, how hot is the temperature, or how hot is the reaction. I think expecting it to stop at the acetal is a little bit risky, but you can show it as 2 separate steps on paper though. Okay. So I'm just drawing it out this way so that we can see that after we do the protonation, eventually the acetal is going to fall back off and we're going to get the final product we wanted. Okay. So questions about this? Yeah?
So we can't show it in one step with the H3O plus and the heat?
Oh, you totally can. Yeah. Yeah. Yeah, so you can draw it out as like a separate intermediate or just going all the way to the product, and I'm fine with either. Okay. So, yeah, I guess other questions about this before I go on to some more details about the exact hemiacetal.
You okay with this? For things like this, listing our acid as H plus?
Mm-hmm. Yeah, if you want, you can write H2SO4, but people write it as just ROH, H plus so frequently that that's kind of not a big deal if you do. Yeah. Okay, so a few different specific details about this. One problem is that acetals are not the most robust protecting group. They have an unfortunate habit of falling off if there's any water around, theoretically, so sometimes that's good because you want to deprotect easily. But I guess the whole field of protecting groups in synthesis comes down to like stability versus lability. You want it to stay on there for as long as you need it on there, and then you want it to come off real easily at the end. So these are a little too far towards the labile or like fall apart or react really easily kind of end. So people came up with a way to increase the stability of the acetal group by doing a slight modification. So, oh, yeah, I guess protecting groups are so commonly used that PG is kind of sometimes used to abbreviate them. So if we want to stabilize these things and have them, not leave at the drop of a hat when we're trying to do other chemistry around nearby, we can actually make a cyclic acetal instead. So rather than having two separate molecules of alcohol, we're actually going to use something that is a diol already. So it's basically got two equivalents of alcohol sort of built into the same molecule. And then again, H plus mol sieves. Okay, so tracking this, our same 3 carbons are down here like always, but we're also making a new ring that involves carbons, let's say 4, 5, 6, and 7. We know that this oxygen is going to leave as water during the reaction. So what we're actually making is both of the oxygens from this diol, which is actually ethylene glycol as it turns out, end up bonded onto the carbon here. If you're having a hard time seeing that, working through the mechanism with this molecule might be a good idea. And then that kind of loops around and you get to the other oxygen of this compound, which is also bonded onto the central carbon. So you basically end up making this ring that's got 2 oxygens bonded onto the carbon of where the carbonyl used to be. So a good way to check that you're doing this right is carbon 2 here, what used to be the carbonyl carbon, starts out with 2 bonds to oxygen. It had better end up with 2 bonds to oxygen. Okay, and then getting it off works exactly the same way as hydrolyzing any other acetal. So like H3O plus, maybe heat if you want, and then that's just going back to where it started. Okay. Cool, so I got a couple minutes left. One other option that we do have that we haven't looked at too much for sulfur chemistry is you can also do all this with thiols. So not just the cyclic acetals, but also like the regular acetals. But it's basically exactly the same reaction, just this acetal and then, or this carbonyl, and then a dithiol. And then you're actually making a ring with 2 sulfurs in it. You can use hydrolysis to get that back off. The only benefit of this is something that we're not explicitly going to cover, and that is there are actually other ways of getting this off that will deprotect this one, but not deprotect acetals. So okay. So the reason that this is more stable, the cyclic acetal compared to the acyclic acetal, really just has to do with, I guess, the proximity effect, which we saw a little bit of in OChem 1. Basically, if you accidentally start hydrolyzing this at the wrong time, like if the ring pops open and one end of this thing is sort of flailing around with its OH on there, at least it's sort of tethered nearby and is still attached to the molecule. So it's a lot easier for the ring to like close back down and go back to being the acetal than it would be if you had 2 separate OR groups and one of them just went off and was gone completely. So these are usually going to be a little bit more robust and going to stick around longer and not accidentally deprotect when you don't need them to. So usually if you have to pick a protecting group, people are almost always going to show sort of the acetal as a cyclic acetal protecting group instead of this acyclic one up here. Okay. One last thing that I do want to show that, do we have time? I got like a minute. Okay. And that is, be on the lookout for this happening in a way that we're not expecting, because one real common problem that people like to mess you up with is, here's a molecule, here's acetone, what's going to happen? You're looking at this and you're like, I have no idea, but you do have a diol and you do have a carbonyl. So this is actually going to make an acetal, even though it's upside down from what you're used to seeing. So basically, take all this chemistry up here, flip it upside down. This molecule is pretty much doing the same thing as this ethylene glycol up here on the arrow. Okay, so be on the lookout. If you've got a diol and a carbonyl, it can do this even in ways you're not used to seeing exactly.
Can I ask a really quick question about acetal?